Well, dear students, so see, this is thermodynamics, and this is one of the most important and conceptual chapter of your chemistry. This will make the foundation for your thermodynamics, equilibrium. Means this chapter will make the concepts for equilibrium, chemical and ionic, both equilibrium. All the concepts derived from this chapter only. In class 12th, your electrochemistry, solutions, and colligative properties, all concepts for all the chapters were developed from this thermodynamics. So, all of you, if try to understand physical chemistry, you must be focused here in this chapter. Try to understand the things, the concepts, what I'm going to explain here. So first we see a general overview of this thermodynamics. What thermodynamics basically explains. So thermodynamics describes, basically this describes, point wise I can make this, describes, thermodynamics describes microscopic properties of microscopic properties of properties of equilibrium system. Equilibrium system. That's why sometime systems, right? Sometime I used to define this thermodynamics as the branch of science which deals the systems under equilibrium, and all those properties which are observed under equilibrium are said to be thermodynamically controlled properties. So I mean, in the past many times I have discussed these kind of concepts, what are thermodynamically controlled properties and what are kinetically controlled properties. So all of you are knowing this. So thermodynamics deals the systems under equilibrium, and slowly you will understand what is the meaning of equilibrium, right? I will explain this system. So I will define what is system. Just I am giving you first overview of this chapter, right? So system, how to define system. To understand any concept, concept of system is very important. If you conceptualize exact system, then it is very easy to define all the properties related to that system. Second important point of thermodynamics is it is empirical, entirely empirical, right? It is entirely empirical, empirical, right? And third point is basically built on this. Total thermodynamics is built on built on four laws. Means total thermodynamics is built on these four laws and simple mathematics. Simple mathematics, right? So This total thermodynamics, it is based on, basically built on these four basic laws, also called laws of thermodynamics, and some simple mathematics. I have put it here simple, right? Not complex mathematics is not required here, right? Only some differentiation and integration is required. That's it. Now see, zeroth law, zeroth law, this zeroth law defines temperature, defines temperature T. I have already talked about this in the previous chapter, gaseous state. First law, first law, this defines energy, defines energy or internal energy. This is represented with E or U, E or U, right? Second law, this defines entropy, entropy represented by S. And third law, this defines or gives or enables us to get the numerical value. This will gives the numerical value of entropy, right? Numerical value to entropy. To entropy. So basically, these are four laws which I mean on which this total thermodynamics is based, along with some mathematics is involved. And one important point I should mention here, that these laws are these laws are universally universally valid. These laws are universally valid, and they cannot be circumvented, right? They cannot be circumvented. So all these laws are universally valid, right? These laws are universally valid, and they cannot be circumvented, cannot be circumvent it, right? So note down this point. This is okay. So this is the overview of this whole chapter. So on the basis of all these four laws, the total thermodynamics can be explained. Now see some definitions, and after that slowly we will come to the one by one laws, right? So some definitions, important definitions. Definitions. First definition is system. Although all of you are knowing, system is the part of the universe. This is the part of the universe, part of the universe which is under observation. This is under observation. Observation, right? So system is the part of the universe which is under observation. Suppose that if you have taken a container and have taken some matter here, so this part of the universe is under observation. So this is system, and rest part of the universe is called surrounding. Surroundings, right? So rest part is surrounding, and this specified part is the system, right? So surroundings is the next definition, part of the definition. So surrounding is the rest part of the universe except system. So surrounding is the rest part of system, right? So rest part of the universe except system. Universe, right? Except system. And boundary the surface which divides system from surrounding. Boundary, the surface dividing the system from surrounding. From the surroundings, right? So these are the simple, I mean, definitions of system, surrounding, and boundary. Okay, good. Now, system can be classification of system. Systems can be of different types. So system can be, number one, open. So in open system, mass and energy both can be both can transfer can be transferred between system and surrounding. Between system and surrounding, right? For example, if you see, if you take open container like this, one part is open, and if you take some suppose that if you take water at suppose that 80 degrees Celsius, this is water, and this is our system, and this is surrounding. Let the this surrounding has the temperature what, let it be 20 degrees Celsius. So surrounding is at 20 degrees Celsius, and our system is at 80 degree Celsius water in which. So you can observe, you can see cup of tea. If you take cup of tea, then vapors are coming out. Vapors coming out means mass is going to the surrounding. Mass is going to the surrounding, and temperature also down. So heat is also transferred between the system and surrounding. So here, so mass is transferred from system to surrounding. Vapors are coming out, right? So mass is coming out, and along with mass, energy is also transferred in the form of heat. Matter is also energy. If matter is moving from one place to other place, definitely energy is changed, because energy depends on mass as well. So along with the mass, some energy changes, and due to transfer of heat, because there is a temperature gradient between system and surrounding, so heat also transferred from system to surrounding. So some heat, the net heat transferred between system and surrounding. So heat change means heat energy, and mass, and along with mass, some energy also changing, because energy depends on mass also. So open systems can exchange both energy and mass with the system, with the surrounding, right? Second is closed system. Closed. So now I think it is clear. Once you understood this open system, now you can very easily understood a closed system. In closed system, there is no change, there is no exchange of mass between system and surrounding. So suppose that if you were taken water, same at 80 degrees Celsius, so 80 degrees Celsius water you have taken, water vapors will be confined here, no problem, but they will not escape out, so mass will not change, so energy can transfer between system and surrounding. So you can say, and in the form of heat, right? So heat energy will be transferred between system and surrounding. Okay, surrounding is still 20 degrees Celsius I have taken. So heat energy is transferred between system and surrounding. So closed system, energy can be transferred, energy can transfer, can transfer transfer between uh, system and the surrounding, and the surrounding, right? But not mass, but not mass. So this is called closed system. Now next one is, third one is isolated. Isolated. So in isolated system, this wall of this is made up of some material which do not allow the transfer of heat, and such type of material are said to be adiabatic material. Adiabatic material. And if you have taken water at 80 degrees Celsius, 80 degrees Celsius water and here 20 degrees Celsius, there is no heat transfer between system and surrounding, right? No heat transfer, and it is closed. So neither heat nor mass transferred between system and surrounding, right? So neither heat, neither energy nor mass mass can transfer between can transfer between system and surrounding. And the surroundings, right? So we can say thermos is the good example, but cannot say best example of this. So thermos flask, it is a good example but not the best. Best example is universe. Universe is the best isolated system, right? Because from universe energy will go where we do not know, right? So universe energy and mass total I mean is conserved, right? Well, so we have discussed type of system. We have three types of system: open, closed, and isolated, right? Now, see what parameters are required to describe any system, right? So, what different parameters we should require to define any system? So, describing systems systems requires number one, a few macroscopic properties. Macroscopic properties, right? So microscopic properties of system that is required. So those are pressure, volume, temperature, temperature, number of moles, and mass. So the fundamental variables which are required to define any system are P, V, N, and T. Already we have talked about these variables in gaseous state. Next is knowledge of system, knowledge of system, whether it is homogeneous, whether it is homogeneous or heterogeneous, or heterogeneous. So I mean, you don't require this heterogeneous system because heterogeneous systems are not in your syllabus. So whenever at your level you are trying to apply the thermodynamic concepts, so every time your system is homogeneous, should be homogeneous. And if it is not mentioned, then by default your system is homogeneous. Otherwise your formulas are not applicable. Means PV is equal to nRT. If you want to apply, then your system should be homogeneous. Right? In your system, what is the meaning of homogeneous? That in the whole system, like suppose that if you take pressure, so pressure should be constant every point in your system. Temperature should be constant. It is not valid that you have considered one system, and in one system in different region temperature is different. This is not possible. And if this type of system is there, then that is not in your syllabus. That is heterogeneous system and it is not included, or this is not in your syllabus. Knowledge if system is in equilibrium, right? Knowledge if system is if system is in equilibrium state. What is the meaning of equilibrium state here? The meaning of equilibrium state is all these variables are constant with respect to time. So the meaning of equilibrium state is that all microscopic properties are constant uh, constant with respect to time. So if in any system, this is the general meaning of equilibrium. More fundamental meaning of equilibrium. Suppose that if you have taken any homogeneous system and all these variables P, V, N and T are constant with respect to time, then you can say that your system is under equilibrium. So at equilibrium, all these properties are what? Constant. All these microscopic properties are constant with respect to time. Now, one more thing. So, if P, V, N and T with respect to any system are constant, then what will happen if someone asks, okay, what about partial pressure? Your answer is constant. What about if someone is asked, what about mole fraction? Constant. What about if someone is asked, okay, what is the status of density? Your answer is constant. Because you know all these properties or any property which is defined with respect to all these variables, all are constant. Concentration, because you know N by V, moles per liter, N by V. N is constant, V is constant, so N by V is also constant. So in a system, if PV and T are constant with respect to whole system, definitely with respect to every component, this is constant. So once all these variables are constant with respect to time, you can say that your system is under equilibrium state. And this is the perfect definition of equilibrium state, right? And one more information you must know about your system. So then you can perfectly describe any system. That is the knowledge of the number of components. Knowledge of the number of components. Number of components. Right. So if you have all these information regarding any system, then you can fully describe or define any system. Understand? So microscopic property you should know. I'm not telling that these all properties should know. Suppose that there are four variables. I have written here mass, but if you have this number of moles, then no need to specify the mass. Four variables if you have, and if you are knowing three variables, then fourth don't require the fourth variable, because all of you are knowing that we have a equation PV is equal to nRT. So if in that equation you have identified three variables, then fourth variable you can very easily calculate. So no need to specify all four variables, but few of macroscopic properties you should know to define any system or describe any system, whether it is homogeneous or heterogeneous, whether it is in equilibrium or in not in equilibrium. And if it is not in equilibrium, you cannot use PV is equal to nRT, you cannot use any other thermodynamic equation. Like thermodynamics first law, you have relation delta E is equal to Q plus W. That equation is applicable only when your system is under equilibrium. If your system is not under equilibrium, you cannot use. Right? So whatsoever formula we are going to develop here, we are going to derive here, all those formulas are valid at equilibrium, means when all these properties are constant with respect to time. This is very important point, and this is throughout your physical chemistry, whether it is equilibrium state, chemical equilibrium, ionic equilibrium, solutions and colligative properties, electrochemistry. Every chapter involves the concept of thermodynamics, right? So this thermodynamics is an important tool to understand chemistry, right? To understand chemistry. And see what is the meaning of the number of components. We should know this. See, number of components means chemically independent components. Chemically independent chemically independent components or species. Suppose that if you have taken water in a container, only pure water, nothing else. If you have taken pure water, so in this pure water, the number of components is 1. Pure water, component is 1. Component 1. Similarly, if you take glucose and water, solution of glucose, then glucose is one component and water is another other component. So this is the meaning of component here, chemically independent species. So how many chemically independent species are there in your system? That is also requires to define any system. So hopefully all of you are clear what are the different parameters required to define any system. Okay, good. Now come to the next definition, that is the properties. Properties. Properties or physical quantities, you can say, or physical quantities. Quantities. So major two class of properties or two class of physical quantities we have. First one is extensive. Extensive. Already I have discussed about this extensive. So what are extensive? Again, we can do the revision. Extensive means changes with the subdivision of the system. Extensive physical quantities are changes with subdivision of system. Or another definition you can use, additive in nature. Additive in nature, right? So if additive in nature, then definitely they are subtracted as well. So you can subtract them. So extensive properties are changes with the subdivision of the system. Means if you divide any system into or more parts, then extensive property according to that they will change, right? For example, mass, volume, energy, enthalpy. Enthalpy is represented by H, energy is represented by E or U, right? Entropy, S, gives energy, G, right? Etc. Second, intensive. Intensive. So just change this meaning of, I mean definition, you can change this, changes with the subdivision of system. So these intensive properties are independent of subdivision. So they are independent of subdivision. Subdivision of system. And or non-additive in nature. Non-additive in nature, right? So intensive properties you cannot add or subtract. This is very important. For example, see temperature. Temperature is intensive. Temperature T is intensive, right? So we cannot add or subtract this temperature. See how to understand this. I'm going to give you one example. Suppose that you have water here at 80 degrees Celsius, H2O you have, and in another beaker you have water at 20 degrees Celsius, right? and suppose that these two are mixed together. Okay, and if someone is asked, okay, what is the temperature of this mixture which is obtained? So temperature of this mixture, you cannot write 80 plus 20. This is incorrect, right? Means you cannot directly add the temperature. And you know, this chemistry, in every next problem, we are dealing with the mixture, right? Because you know, if you consider any chemical reaction, then what is chemical reaction? Chemical reaction is definitely a mixture. One or more components you are taking, and during the course of reaction, whole system is the complete mixture, and even after the completion of the reaction, you again get the mixture. So we are here to deal with the mixture. So this type of properties are very important to understand. First, temperature, you cannot add directly. If 80 degrees Celsius is here, and you are doing such type of problems right from your class 9th and 10th. So we have two types of properties. One, suppose that if we are talking about the mass, 10 gram here, 20 gram here, so you simply add, and okay, this mass is additive. If we take here 10 moles, here we take 5 moles, so we can write here 15 moles. So moles you can add, volume you can add, mass you can add, energy you can add, but you cannot add temperature. So this concept is so important for physical chemistry, that which physical quantity you are able to add in the mixture and you are not able to add in the mixture. And in chemistry, most of the time we are dealing with the mixtures, right? So what we are doing here, we are using principle of calorimetry, heat loss, heat gain. Means we are calculating the temperature in terms of heat, and heat is extensive. Heat is extensive. Heat energy is extensive. So we are, what we are doing? We are doing here multiplying this temperature with the mass and heat capacity C. So MC and delta T, that will gives you a heat. Now you can add or subtract the heat. So this is the meaning of non-additive here. All of you are getting my point or not? Right? So temperature is non-additive. Like temperature, pressure is also non-additive. Pressure is also non-additive. So you cannot add or subtract pressure. And suppose that the temperature here, this whole system has temperature 80 degrees Celsius. If we subdivide this system, see, independent of subdivision of the system. So if we divide this system in any part, any fraction, every fraction has temperature 80 degrees Celsius, because this temperature will not change. Suppose that you are sitting in a room, thermostatic room, and the whole temperature of your room is 25 degrees Celsius, and if you divide your room in two parts, temperature same. It is not like that 25 by 2 for one part and 25 by 2 for other part, right? So like temperature, pressure, then someone of you may raise the question, okay, sir, what you are doing in the case of Dalton's law of partial pressure, in which you are writing like this. So see, dear students, this is a science. This is not so simple as it looks, right? Here I am writing this P mixture is equal to PA plus PB, but basically here I am not adding the pressure. It is by default added here. We are adding moles there. to derive Dalton's law of partial pressure, if you remember in the derivation, clearly I have shown you that I am adding moles. I am not adding directly pressure. Since temperature is constant, volume is same, so it appears that we are adding pressure. Final expression which we are getting, that includes this, but actually this expression we are getting by adding moles. So such type of expressions, many expressions you may get in physical chemistry, that it appears that we are adding here pressure, but it is not the truth. The truth is this equation is obtained by adding moles, not directly by adding pressure. So you cannot directly add the pressure, right? In one container some pressure of gas is there, in some other container some pressure is there, and if both are joined and you say okay P1 plus P2, you never ever you should write. This is a totally wrong concept, right? But I mean, it appears if you start from here, from this expression, then you can say, okay, here we are adding pressure. What is the problem, right? So the problem is the not understanding of the scientific concept. The problem is that if you are any moment of time, if you are explaining this Dalton's law of partial pressure from here directly by writing this, means you are not aware of the concept, right? So temperature, pressure, so T, P, all types of concentration terms, all types of concentration terms, concentration terms like percentage, molarity, molality, mole fraction, density, etc. Right? Heat capacity, yeah, sorry, specific heat, etc. So these are what intensive properties. Similarly, one more property is popular, but this is not different from first two. It is somehow related to the second property. This is a molar property. Molar property. So molar property, you can obtain molar property. Uh, it is written by putting a bar here, and this is equal to x by n, right? Where this x dash is called molar property. This x is extensive property, and this n is number of moles. Number of moles. So if you divide any extensive property with the number of moles present in the system, then you will get molar property, right? So molar property is the property which is obtained by dividing any extensive property with the number of moles present in the system, right? And you know this all molar properties are intensive in nature. Intensive in nature. right? So all molar properties are intensive. So basically we have two types of properties, extensive and intensive. For example, if you take volume, so volume is extensive. But if you divide any volume with the number of moles present in the system, then you will get V bar, and this is called molar volume. Molar volume. So molar volume is intensive. Molar volume is intensive, right? Similarly, if you take energy, this is extensive. But if you take molar energy, this molar energy molar energy, this is intensive. Means energy of any system will change with the subdivision. If you subdivide any system in different parts, then energy accordingly will distribute. But energy per mole, that is intensive, that is independent of subdivision. So when you have a system, right, it has some energy. So sometimes what we do to make the calculation simple, we always try to express the quantities in terms of molar quantity. We deliberately made the quantity intensive so that if you take some portion of that from that system, the property will not change. So during the making of definitions, many definitions in thermodynamics or in physical chemistry, we deliberately made this physical quantity intensive, so that if you do the experiment with some small quantity, or if you are doing the experiment with the large quantity, there is no change on that standard values, right? So sometimes we deliberately convert this extensive property into intensive. And think, if all the physical quantities are defined in the extensive manner, then the whole calculation is very simple. Hmm? If every time temperature is relative, how simple is the calculation that, okay, 80 degree and 20 degree are mixed, final temperature is 100 degree. But it is not like so. It is not so simple that you just add these two and get the final value in the mixture, right? So this is all about uh, different types of properties. Molar property, extensive, intensive, right? So these are the physical quantities, and in different chapter, when I will discuss different properties, I will let you know that whether it is extensive or intensive. But you should be careful that if any property, like suppose that it is given molar conductance, so molar word if added, immediately understood, okay, this is intensive property, not extensive. And you have to apply all the features of extensive properties on the molar properties, independent of subdivision of the system and non-additive in nature, right? Well, dear students, let's see the state of system at equilibrium. So every state is defined under equilibrium. As you know, equilibrium, what is equilibrium? When all the variables are constant with respect to time, and that represents a state. Already I have discussed this meaning of state, but again I am revising this for you people. So this state of system at equilibrium defined by, this is defined by the collection of the collection of all macroscopic properties, all macroscopic properties. properties that are that are described by described by state variables. State variables. What are state variables? State variables, we have P, V, N, and T. So state is defined with the fixed values of P, V, N, and T. And you know, this is independent of the history of the system. What means? It means, so fixed value of this represents a state. This represents a state if the values of P, V, N, and T are constant with respect to time. So this represents a state of your system under equilibrium, because this is the condition, this is the requirement for equilibrium as well. If P, V, N, and T are constant with respect to time, then that is the condition for equilibrium, and that represents the state of your system. Okay, and you know, this state of any system, this is independent 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 of the history of the system, right? So this state of any system, this is independent of the history of the system, that how we bring this system, means how to raise the temperature, how to raise the pressure, all these state functions are what, independent of this history, right? So state is defined with the definite values of P, V, N, and T. If all these are constants with respect to time, then your state of system at equilibrium, right? And one more important thing is here, that for any one component system, for any one component system, right? What the variables are required to define the system for any one component system? What variables are required to define the system? So the answer is first, N is mandatory, moles, and see, we have four variables P, V, and T. So this is mandatory for any one component system. If you want to define, N is mandatory, and two variables, two variables, right? For example, if you want to explain this volume, so to explain the volume, you require N, right? And any two variables, so except V, P and T, right? So we can say that to define any system or state of any system, we require maximum three variables. N is mandatory and rest two. Similarly, uh, P is equal to, P is the function of, we can write N, T and P, right? So these are the representations. How to calculate the different properties, or what the variables are required to define any system. So we have four fundamental variables P, V, N and T. So for any one component system, N is required and two variables are required. This is not always true for two component or three component systems. Some more variables are required for that. So see here, we generally, consider one component system, right? Because major systems, what is, in your syllabus, that is one component system. Now see how this notation, what is the notation of this notation, right? So notation, how to express the state of any system. Notation means how to express the state at equilibrium. For example, suppose that 3H2 gas 1 bar 100 degrees Celsius, right? So see the representation. This is the representation of state, right? This is the representation of state. Now see, what is this 3? 3 represents here 3 moles, means N is equal to 3. So whenever you are going to express or represent any state, you have to follow this method to express or to represent the state. G means gas here. This is also very important. You have to mention whether the given substance is gaseous or liquid or solid. See, this is pressure. P is equal to 1 bar, right? And this is temperature. T is equal to 100 degrees Celsius. So this represents state. All these points are mandatory. See here, I have not here included the volume because it is not required. Only three variables are required: temperature, pressure and moles, quantity, right? And phase, obviously this is understood here. Phase you have to mention, right? So similarly, another example like 2Cl2 gas 5 liters and 50 degrees Celsius. Now this is also represents state, right? See here, moles, gas, volume, temperature. This time pressure is missing, but that is not required. If at any moment of time, if you want, you can calculate what is the pressure. But why, if we are apparently knowing that value, then what is the need to represent here? So there is no need to represent any state by putting all four variables. The only requirement is three variables, right? Similarly, you can write 5 carbon graphite solid and 5 bar and 50 Kelvin. So see, this is also a representation of state. This is moles, 5 moles, graphite and solid. This represents its phase, that it is a solid, because you know carbon has different allotropes. So you have to mention that it is diamond or it is graphite. Otherwise, as per the notation, it is incomplete, right? These are the fine points you require to represent any state. Here pressure is there and temperature is there, right? So this is how to represent the state. So temperature is there, pressure is there, moles are there. No need to include what volume here. So this is how to represent, how to express any state and what is the requirement, right? So this is I mean state of system and how it is represented. Okay, good. Now see change of state, right? Change of state. Change of state, or you can say transformations, right? So see how it is noted. Notation, see 3H2 gas, 5 bar, 100 degrees Celsius. Suppose that this is initial state, initial state, right? And 3H2 gas, 1 bar and 50 degrees Celsius. So this is final state. So in this way you can express the change in state, right? Change in state. Now see what the parameters are changing. See pressure here 5 bar, so here pressure is 1 bar. Temperature here 100 degrees Celsius, here the temperature is only 50 degrees Celsius. So these two variables are changing and therefore the state is changing. So what is the meaning of change in state? Change in the state variables. Minimum 2 variables should be changed there, right? So it is, I mean, in your syllabus, it is very rare that three variables are changing simultaneously, right? Mostly you will get change of 2 variables, right? So this is the meaning of change of state. Okay. So we have developed the concept of state here in this lecture. Change in state, different important definitions, different type of properties, and in the next lecture we will discuss different types of process, what is the path, reversible, irreversible process, state functions, path functions, like that, right?